Hello, Corey again, and we're going to talk about section 1.4, collecting data to understand causality. So causality means what causes something to happen and can be understood in terms of two variables. So the first one is the treatment variable. So whether or not a specific treatment is used. So in our textbook, we have a person who drank peanut milk, and I'll talk about this a little bit later, and then an outcome or a response variable with whether or not a certain outcome is seen. So like a person's gum disease is improved. So causality is to determine whether the treatment variable causes a change in the outcome variable. So in the textbook, there's a story about a man I think in San Francisco. He would drink peanut milk, and he claims that his gum disease improved because of drinking peanut milk, and not. But there's a bunch of different factors that could have helped improve his gum disease, like brushing his teeth, better eating habits, or better diet. There's a bunch of different confounding variables that we didn't eliminate by, and we'll talk about eliminating those a little bit later. So that would be an example of a claim of causality. So there are the groups. The treatment groups are the individuals who receive the treatment. That should make sense. Treatment group, receive treatment. The control or comparison group is controlled, so they won't receive the treatment. So an example of this is to see if online homework improves students' grades. So we're going to split 550 students using online homework as a treatment group and 550 students not using the online homework as a control group. And we're going to observe the different grades between those two groups. So controlled experiment and observational study. A controlled experiment consciously places participants in two groups, which are the treatment and control groups, and records the differences. These researchers take control by assigning the subjects to the control or treatment group, and only these controlled experiments can establish a cause and effect relationship. That's very important. Controlled experiments are the only ones that can establish a cause and effect relationship, while observational studies use groups that are already created and records the differences. Researchers don't assign the subjects to groups, and the subjects are put into the treatment group or the control group either by their own actions or by the decision of someone who's not involved in the research study. So a way that researchers assign people to different groups is the use of a random assignment. So they could use a computer or other methods like rolling a dice, flipping a coin, or picking a card to randomly assign the participants to the control and treatment groups. That would be a random assignment. And an example of this is flipping a coin. The heads means the participant. So like as they come across heads, okay, you go to the treatment group. Flip tails, you go to the control group. And then another example of this, you could have you could assign numbers to all the participants in your study. Put the numbers in a hat, shuffle them, shuffle them, shuffle them, draw, and then have one go to the draw for the treatment group, and then go for draw for the control group. It's another example of randomized or random assignment. In controlled experiments, a well-designed one should have very large sample sizes to observe the full range of variability in the subjects. And an example of this is determine whether exercise leads to weight loss. Due to testosterone, usually men can lose weight much quicker. So if we're going to do an experiment, we better get a large enough sample so we can cover the variability in these subjects, and also genetics. Some men may not be able to lose weight as fast as other ones, and then women, they're going to be on the same effect too. So the subjects should be assigned to treatment and control groups randomly, and make all the conditions as similar as possible for the groups, Unless the groups of the study are identical in every way except for the treatment, we cannot conclude that the treatment causes the outcome. So it's very important to use controlled experiments to determine if you want to determine causality. So here's an example. A study looked at the effects of light on female mice, and 50 mice were randomly assigned to a regimen of 12 hours of light and 12 hours of dark. And while another 50 mice were assigned to 24 hours of light, which is denoted as LL in this column, researchers observed the mice for 2 years. The accompanying table summarizes the results. And then these are the number of mice that developed tumors or didn't develop tumors, just matters which row and what. So I would pause the video right now and answer these questions. Alright, so A, we're going to determine the percentage of mice that develop tumors from each group. So to determine the percentage of mice that develop tumors from each group, we're going to 4 divided by 50, because that's how many are in this LD group, and that equals 8% if you multiply it by 100, and then the L, this would be 28%. So we can see the difference already there, and then we'll see it on the next slide. Was this a controlled experiment or an observational study? How do you know? Well, it's going to be a controlled experiment because one signal to tell you it was a controlled experiment was the use of random assignments that allows you to capture the large amount of variance too. So can we conclude that light for 24 hours a day causes an increase in tumors in mice? Why or why not? Yes, because we use random assignment, or a controlled experiment, I'm sorry. And by using a controlled experiment, we can determine cause and effect relationships. And here's all the official answers. So 8% for LD, and then 28% for the LL. A controlled experiment, yep, you can tell by the random assignment. And then the third question, yes, we can conclude cause and effect because it was a controlled experiment and random assignment was used. Alright, another example. A study reported on the effects of vitamin C in breast milk for breastfeeding mothers. The children whose mothers had chosen to take high doses of vitamin C had a 30% lower risk of developing allergies. So the 2 questions I want you to pause and answer are: indicate whether the study is an observational or a controlled experiment, and can you conclude that the use of vitamin C caused a reduction in allergies? Why or why not? Alright, so the answer to A is going to be it is an observational study, and how I know this is there's no mention of random assignment or control and treatment groups. And then B, can you conclude that the use of vitamin C caused a reduction in allergies? Why or why not? No, we cannot, unfortunately, because we didn't perform a controlled experiment. We performed a observational study. So here's the official answers. This was an observational study. We cannot conclude cause and effect from observational studies, and we cannot conclude that the use of vitamin C caused a reduction in allergies because the researchers did not randomly assign mothers to treatment and control groups. This step is necessary for identifying causation. So another thing we need to talk about is bias. Bias may occur when the assignments are not random. The controlled experiment does not use, so like for instance, the controlled experiment does not use random assignment. An example would be to determine whether exercise leads to weight loss. So a researcher puts the heaviest people in the exercise group. Well, that's going to be biased. And then another example, giving tutoring to the first 15 who register for a 30-student class to see if tutoring helps with the exam scores. This is biased since early registrants are likely to be better students because they're probably more proactive in their studies and outcomes. So a group of elementary school children took a vocab test. It turned out that children with larger shoe sizes tended to get higher scores on the test, and those with smaller shoe sizes tended to get lower scores. As a result, there was an association between vocab and shoe size. Does this mean that learning new words causes feet to grow, or that growing feet cause vocabulary to increase? The fact that the shoe size and vocab are associated does not mean that changing one variable will cause the other to change. That sounds crazy, and it should sound crazy. Like, if you know a lot of vocab words, I don't think your shoe size really changes. And then the same thing, your shoe size. If you have a large shoe, it doesn't mean that you know more vocab words or whatever. So I think that's crazy. And association is not the same as causation. In general, when two variables are associated, we can conclude that changing the value of one variable will cause a change in this other variable. And so continuing to speak about association is not causation. A confounding variable, a factor, is a characteristic other than the treatment that causes the outcomes. The groups may experience different outcomes because of the different characteristic and not because of the treatment. So, for example, people with gray hair are observed to have more wrinkles. This does not mean that gray hair causes wrinkles. Old age causes both gray hair and wrinkles. So we can see that old age is a confounding variable. And then another thing is, what's funny is one of the fathers of modern statistics actually tried using this association as not causation phrase, and his name was R.A. Fisher. He said that just because smoking and lung cancer rates were associated did not mean causation. And he actually said he would flip it around and saying that by getting lung cancer, you're more likely to smoke because it takes away the pain. And we know that's proven to be false. Smoking does actually cause lung cancer. So it just kind of shows you that even the quote-unquote the father of modern statistics can get these things wrong. So another thing, anecdotal evidence is not science. An anecdote is essentially a story that someone tells about his or her own experience. So an anecdote should never be used to make a statement about groups of people. It is not useful for reaching conclusions about cause and effect relationships. So an anecdote would be, if Jack drank peanut juice and noticed that he became healthier, that doesn't mean that that the peanut juice makes people healthy. He probably was following a more strict diet, a better diet, took better care of himself, probably exercised. So you can see that anecdotes aren't science or aren't evidence to prove things. Another thing that we need to talk about in this section is the placebo effect. A placebo is a fake treatment, like a harmless pill or a sugar pill, that looks like the treatment being tested. And the placebo effect is a phenomenon of reacting after being told of receiving a treatment, even if there was no actual treatment given. So an example is, after being told by a doctor that an empty capsule will treat the patient's fever, the patient's temperature decreases. So, and then another example referring to the peanut milk. So if we actually really wanted to study that, whether peanut milk increased gum health, we would want to use a placebo, one that smelled, looked, and tasted just like peanut milk, but isn't actually peanut milk. So if those people in the placebo or control group had increased gum health, then we wouldn't be able to determine the cause and effect relationship. Um, a single blind study is a study where the participants do not know whether they are in the control group or the treatment group. So there's only one, so single, one group of the study that doesn't know. While double blind is a study where both the participants and the person administering treatment or the researchers or the doctors in some cases do not know who is in the control group or who is in the treatment group. So you can see that there's two groups that are blind per se to the study. So participants don't know which group they're in, and the person doesn't know, or the researcher doesn't know who is in either group. So here's an example of a double-blind study. To determine whether exercise leads to weight loss, first we might know who is in which group. This means that when we interact with a participant, we might consciously or unconsciously treat that person differently, depending on which group he or she belongs to. So for example, if we believe strongly that exercise helps with weight loss, we might give special encouragement or nutrition advice to those who are in the exercise group that we don't give to those in the control group. If we do so, then we have biased the study. Second, we must consider the participants themselves. If they know that they are in the treatment group, they may behave differently than they would if they knew nothing about their group assignment. Perhaps they will work harder at losing weight, or perhaps they'll eat much less or much more because they want to believe that the extra exercise allows them to eat anything they want. So here's some elements to create the gold standard for experiments. First, we need a large sample size, and then the next element is controlled and randomized. Random assignment of subjects to treatment or control groups minimizes bias. And the study being double blind is another element of the gold standard. So that means that neither subjects nor researchers know who is in which group. And then the fourth element is that implementing a placebo when it's appropriate would be the last element of the gold standard. Alright, so an example of determining cause and effect relationships. Crohn's disease is a bowel disease that causes cramping, abdominal pain, fever, and fatigue. A study reported in the New England Journal of Medicine tested two medicines for the disease, the injections of Inflix and Azath. The participants were randomized into three groups. All groups received an injection and a pill. Some were placebos, but still a pill and an injection. So one group received only the Inflix with a placebo pill. One group received the Azath with a placebo injection, or the one group actually got both the injection with Inflix and the pill for the Azath. And so a good outcome was defined as the disease being in remission after 26 weeks, and the accompanying table shows a summary of that data that this study yielded. So, two questions for you. Compare the percentages in remission for the three treatments, and which treatment was the most effective and which was the least effective for this sample. And then B, can we conclude that the combination treatment causes a better outcome? Why or why not? And these answers will kind of tell the story. Alright, so the solutions for this example, for the combination, 96 divided by 169, so the remission divided by the total in the combination group was 56.8% success. And then for the Inflix, 75 divided by 169, because that's how many were in the Inflix group. And then for the Azath, we have 51 in remission and 170 in the Azath group, or for 30% success. So the combination treatment was the most effective for this sample, and Azath alone was the least effective. So we can conclude that the combination group causes a better outcome than the single drugs, which are Inflix or Azath alone. And the study was placebo-controlled and randomized. The sample size was reasonably large, and blinding was not mentioned, but at least thanks to the placebos, the patients did not know what treatment they were getting, so it was an example of at least a single-blind study. And that does it for section 1.4 and chapter 1. Thank you for tuning in, and that is all.